Welcome back. So in the previous video on this reinforcement learning playlist on my channel, the previous video was Q-learning and I introduced the theory. Now we are going to see how this Q-learning algorithm works in action. I will provide you the full MATLAB code that you can code yourself, you can explore. That will be good. I hope this video will be very good for your training. So let's quickly overview what we saw. Basically, we solve this Q-learning algorithm. We initialize Q values, choose if you like to be zeros or some random small numbers. Then take an action. Take the action either randomly with some probability, and I'm going to show how I code this, or take an optimal looking action by using this argument max Q, and then apply it to the system. I mentioned the robot. Robot goes from point S to point S prime. Observe or measure that S prime and compute your reward function. And then update your Q table, basically compute this side of the equation and assign it as the new number to the SA. I discussed that this A prime, you really don't need to know A prime. I am going to show it by hand and in MATLAB in a second. I mentioned this in the video, in the previous video, but today I'm going to show it, so I'm not going to re-mention it. You don't need S prime. And then we repeat step 2 until convergence or the end of so-called episodes. Episodes is, let's say, robot reaches to your terminal state, then restart, then again reaches to terminal state, restart to optimize, how quickly or energy efficient way it reaches to the terminal state. And finally, once it converges or you complete all your episodes, extract the optimal or close to optimal policy by using this argmax command so that you will know the optimal policy. All right, we discussed this more in detail and I was explaining things a little bit slowly on the previous one. I just summarized, that's why I speak a little bit faster. Let's move to the example first by hand, okay? Of course, if you have large states, like let's say robot is moving in a 100 by 100 environment and you have many actions, it is infeasible to do by hand. But to give you a feeling, I choose the same example. We used this in the Q function iteration video as well. So basically we have 3 states. State number 3 is the terminal state. So basically we are looking at our actions in states 1 and 2. Actions is -1 going left or 1 going right. Basically this is the transitioning function from the this Q function iteration video. We really don't need to know here, but I write it here. So robot moves like this, let's say, but all we need to do is apply an action to the robot and robot returns S prime. And robot knows its own dynamics, robot, so basically think about like this. If you are in state 1 here and you would like to go to left, then no, you will stay on your own state since you cannot go left. If you are on state 2 and you basically let's say you are at 2 and you get -1, so your S prime becomes 1. So you move to the first state, or if it is +1, 2 + 1, so S prime becomes 3, you move to the terminal state. And if you're on the terminal state, do nothing basically. There is no action variable here. So reward-wise, a simple reward, since we are introducing these concepts, if you're on the second state and if you decide to go right, since you are going to reach your lovely terminal state, the game is over or the episode will be over, so that you will get a reward since this is what you would like to achieve. I mean, you can, without even reinforcement learning, basically wherever you start, the solution. If you are on the first state, go to the second state, and if you're on the second state, go to the terminal state. So the optimal policy by observation is by If you're on the first one, A is 1. If you're on the second one, A is again 1. 1, 1 is the optimal behavior here. But behave that we don't know this and we would like to calculate. I will show how things work by hand. Suppose you have some values like this in the Q table for state 1, action -1, 1, 1, 2 -1, and 2, 1. In this case, your Q table is 2 by 2, right? So suppose the agent is on the first state, and let's say 25% of the time we choose a random variable, and let's say algorithm choose a random variable which is 1. Basically move from 1 to 2. In this case, how we compute this new value is, first you compute this Q11. Q11 was, you are at basically state 1 and you are taking this random action A1. Its value is 1.2 here. Let's say we use a learning rate 0.1. Why not? Our reward, in this case 0. You only get reward if you are at 2 and taking action 1. So reward is 0. Gamma is 0.9. And you look at, here is this computation, right? This A prime, S prime. So basically, I look at, since my next state will be at 2, sorry for going back and forth, but we have 2 here, right? Robot moves from 1 to 2. And we look at all this two numbers. We look at basically Q2, rows of Q2. One of them is 0.2, other one is 2.4. I am maximizing it, so this number becomes 2.4. As you see, I don't need to know A prime. I'm just looking at the row of the second row of the Q table, which is this, and choosing the maximum one, 2.4, minus the current value, 1.2. And I am assigning, you can do this computation. If you multiply the numbers inside and add 1.2, you are going to get 1.296. So the new Q11 value, after this iteration becomes 1.296. And agent moves to the, agent is now at the second state. And now suppose agent is not choosing randomly. I will show you the logic. And I am looking at argmax. Since I am at the second state, I am looking at which action maximizes my Q table. So in the second state, we have this. The first action has a number of 0.2, and the second action has a number of 2.4. So second action maximizes this Q table. So basically, that gives me A equals to 1, right? So I am going to choose, since second action's number is high, argmax chooses this as 1. You are going to go right. So then I am going to do this computation. I am at the second state and I choose optimally to go right. My current number is 2.4. My learning rate is the same. Reward is 5 because I am at 2 deciding to go 1. So I get a reward of 5. My gamma is 0.9. The third Q table is basically 0, 0. I am not updating because on the third, if you reach to the third terminal state, the game is over, so 0. Minus the current value, 2.4. If you multiply the numbers, if you do this computation, you are going to get, this side becomes 2.66. So the new Q21 becomes 2.66. So a higher number. So this is how we do by hand. I hope how we manipulate things mathematically is clear for your understanding. If not, leave a comment, I will answer. All right, so here is the MATLAB code. You can look at here. It is a short code, has a couple more pieces. Here I am setting up this game in the code. We have this learning rate, discount factor, exploration 0.25. It will mean from the code, I'm going to show you precisely, 25% of the time take some random values, otherwise 75% of the time choose optimal action. I am going to run this for 600 episodes, meaning that 600 times I am going to reach to the terminal state and the game is over. 3 states, left and right actions, initializing Q table to be zeros. This is for recording. I am going to record Q values and plot it for you, so that's why I defined this. This is the reward if I am at second state choosing action 1, 5 of a reward. Then the for loop starts. Basically, I am going to run from episode 1 to episode 600. So this is the reinforcement learning, Q learning algorithm. I start from a random state, excluding the terminal state, either 1 or 2. This is a very simple code, but you can extend. This is the epsilon, this greedy action selection, basically. This rand function of MATLAB gives you a number between on the interval 0 to 1. And remember, epsilon was 25. So if random number comes to be 0.1, which is less than, then I am taking a random action. If it is greater than that, then I am going to choose an action that is the maximum coming from my Q table, whatever maximize this. Right, this means basically arc max a Q S A. So I am choosing the action that maximizes that table. And then I'm going to call whatever I chose here, I'm going to call it as A. And it will choose either -1 and 1 from my actions, left or right. We discussed this in the Q function iteration video. It is better to write it like this, but nevertheless, I wrote it like that. Basically, if you are on the first state and want to go left, you cannot. There is no zero state. You stay. If you are on the first state and would like to go to right, go right. Let's see if I am missing here. This is also a small correction, right? This is if, or if basically you are on the first state and if you would like to go to right, then you also 1 plus 1 becomes 2. And it also, it's basically, I forgot to include that part. So it is more clear from here. This is the basic transition function defined like this. If you're on the second state, go left, go to the first state. Again, in real world, you don't know this. Basically, if you are dealing with a, let's say, robot, you are choosing an action, applying it to the system, and system goes to a new state, then you measure it. You measure it as next, which is S prime, and then you use it for your training. But since we are in a simulation environment, it is inside the simulation environment. Just pretend like we don't know this transition. It's kind of black box, if you wish. Remaining part of the code, basically based on this S and A, I calculate the reward, and this is the Q value update. For that particular state you are in, for the particular action that you take, the same, alpha plus your reward plus gamma. This is the, again, this part of the code is nothing but arc max A prime Q S prime A prime. Again, you don't need to know A prime. You are just looking at the Q tables S prime row and choosing the number with the highest value. Minus this. Sorry, I wrote arc max, but really this is max max A prime Q S prime A prime. We are not choosing the argument action. We are choosing the value, so it is max. My bad. And finally, after this, S becomes S next. I am assigning S to be the, basically new S, new value of S becomes S prime because robot already moved to that location. Then I iteratively go to compute this. This is for recording plotting purposes. At the end of the day, once episodes are over, I am extracting optimal policy like this by using this command. And then I choose my, I extract my optimal actions, which should be 1 and 1, go right and right. Final part of the code is just for visualization, displaying the Q values and then plot the figure that shows how Q values change with respect to each iteration episode. All right, so I choose alpha to be, this 0.1 small learning rate, 0.9 here, and 0.25. So basically, right, remember, alpha is the learning rate, and gamma is the forgetting factor. Sorry, I am recording this late, so I was at university all day. This is Friday. I don't know, either my videos appears on Wednesday or Sunday, at least these lecture series. So yeah, gamma is a discount factor. So let me go back to our little example, and our exploration is to 0.25% of the time we explore. If we do like this, values converge around 550. You can say 400 episodes. It converges, and after it converges, when I extract the Q tables values for basically states, and these are the actions, basically, right, this number is greater than this. So if you're on the first state, choose second action. If you're on the second state, choose second action, or in other words, choose 1 and 1, go right and right, which is the optimal policy that we expect. And if you compare these values with the precise optimal values that we obtain from Q function iteration video, dynamic programming video, this was 4.05, this was 4.05. So we almost convert the optimal Q values. We already converged the optimal policy. Now let's play with this code. Let me now decrease exploration to 5%. So if you decrease the 5%, as you see, if you compare, we already converge around here, but here these are still growing. Our convergence becomes late. So instead of 600, I need to run maybe longer than that, double the number of episodes. And in this case, we got the optimal policy, so which shows the resilience of this method, but these numbers are off, but these numbers are correct. The optimal policy is correct. Just the convergence takes a little bit of time. This actually shows the value of exploration, right? So exploration can allow you to learn better. So let's stick with 0.25, but now instead of using 0.1, let's use 0.5. As you see, we almost converge around 100 iterations, and this is the perfect exact Q table that we obtained from dynamic programming. If I haven't told you, with dynamic programming, you compute the absolutely optimal Q table. When you do Q learning or reinforcement learning, you kind of have the suboptimal policy. But it is known that if you wait long enough, you, as you know from the previous video, you can converge asymptotically to the exact Q table. In this case, this happens. It converges exactly in just around 100-ish episodes, and optimal policy becomes 1, 1. Now let's play with the discount factor. I here decrease it from 0.9 to 0.25. Now it converges around actually 500 seconds. I run this much longer as well. So it converges. The issue is these numbers are off, and which is again shows the resilience of this approach. Optimal policy becomes again 1-1, go right and right, but forgetting factor is small forgetting. Small discount factor. Basically, you more focus on your immediate rewards, so that you don't have a long term vision in the algorithm. So because of that, these numbers converged and they are not going to change if I run more episodes. So that's kind of bad, but again, optimal policy is 1-1. So for this reason, I usually choose a discount factor between 0.5 to 0.9, 0.6 to 0.9, and alpha. For this example, you can choose it. You saw increasing alpha increases the convergence. I still start with a smaller alpha, then eventually increase it. All right, I hope you like this video. More videos to come, so stay tuned, subscribe, and take care.